Okay, we can start to actually speed these videos up. Now that we have gone through an amplifier using an NPN, we're pretty familiar with the mode of operation, and we are simply going through a very familiar process as compared to the last video, but it shows a different type of amplifier. So in the last video, we looked at the common emitter amplifier, and in this video, we're going to look at the emitter follower amplifier. So notice here in the emitter follower amplifier, our output voltage is actually over the emitter, as compared to the previous video where the output voltage was over the collector. And again, we have some DC source, some AC source, some capacitors, an output voltage, and our transistor. Now we know that we need to do DC and AC analysis. DC first. Why? Well, because we need to know what that DC base current is to find R pi. And what is VT? Well, that's the thermal voltage. Now we know that if these capacitors, C1 and C2, if those are relatively large values, then from what we talked about in the last video, we say that impedance is approximately equal to 0, and in the AC analysis, they'll act as short circuits. Otherwise, in the DC analysis, they'll act as open circuits. Now, generally, we're looking for some kind of voltage gain, whether it's closed loop or open loop, some kind of input impedance, and some kind of output impedance. So we can carry through as we normally would with the DC analysis. So our capacitors are going to act like open circuits, and we are going to turn our source voltage to 0 volts. Now if we do that, again, we get some resistors that are hanging off, that are not bounded on each side of the terminals. So we can simplify that into a circuit that looks like this, which looks a little bit like our 4 resistor bias circuit, but we don't have a resistor on the collector. But what we can do is apply our source transform, or our pseudo source transform, to this to arrive at a circuit that looks like this. And from this, again, we can take a KVL around the base loop, get a real nasty looking equation that looks like this, but it's okay because all of these values should be known aside from that DC base current. But we can find that DC base current just by some simple algebra. Now once we know that DC base current, we can find R pi, simply equal to the thermal voltage divided by that DC base current. So let's say that we know what R pi is, we can start to do our AC analysis. So recall that our capacitors are shorted. We take our DC source and set that equal to 0. So we have a ground right here. And what we're going to do is swap our NPN transistor with the equivalent small signal model. Now if we do this, we get a very nicely simplified circuit. Right now it's not so pretty, but we're going to look at the emitter node, E, and we're going to notice if we do a KCL at the emitter node, we're going to have that base current plus beta IV temp that base current, and that's going to be equal to the emitter current. Call it IE, and we're keeping the lowercase here simply because we're looking at the small signal analysis. Now, if we look at the output voltage, well, from the sum of these two currents for IB and beta IB, we know that if we multiply that by the parallel combination of RE and RL, that's going to give us our output voltage. And to find VN, we simply say that VN is equal to VBE plus Vout. That's just a KVL. And what that gives us is that base current times R pi plus that emitter current IE, which we found above right here. Now we can define our voltage gain simply as the output voltage divided by the input voltage. Again, that's the closed loop because we have this load resistor here. And what we get is that the voltage gain is equal to this term right here. So we have beta plus 1, parallel combination of RE and RL. In the denominator, we have R pi plus beta plus 1, and again times that parallel combination. Now notice here that this term in the numerator is equal to this term right here in the denominator. So what we could say is that the voltage gain is equal to 1 plus gamma plus 1, where gamma is some positive value. So we'd say that the closed loop voltage gain is less than unity or less than 1. Seems odd to really call it an amplifier then. So this might be referred to as an attenuator, but if we recall again from the introductory videos, just because the voltage gain is less than 1 doesn't mean the current gain is less than 1. So while this might not be a voltage amplifier, it is a current amplifier, and that is still an amplifier. Now if we look at the input and output impedances, well, we're going to say that Zn is equal to our input voltage right here divided by that input current. And we know that the input current, well, that's going to be the current through these two resistors and then IB. But we can combine these two resistors in parallel simply to get Vn divided by R1 in parallel with R2 plus that base current. Now we can actually define that base current as the input voltage right here minus the voltage of this emitter and that's going to be divided by R pi. Now we know that VE, so the voltage over that emitter, is going to be equal to IB times beta plus 1 times the combination of RE and RL, and that's from the KCL at this node E. So if we find the voltage VE, and we know what VBE is, R pi times IB, we can set up this term, and this allows us to divide by R pi to arrive at a base current that looks like this. So now from finding what IB is, we can plug that in right here, and notice we did this so we could have Vin in the numerator, because we had Vin in this numerator and Vin in the numerator for this input impedance. So that allows us to express the input impedance like this, and we can cancel out the input voltages Vin. So now we can actually determine what that input impedance is if we know all of our values. Now to find the output impedance, call it ZO, we're going to set that voltage source equal to 0, and we're going to remove the load resistor. So if we do that, we end up with a circuit that looks like this. Now notice that we have RS, R2, and R1. That's going to be all in parallel, so we just make that substitution, and then our circuit looks like this. Now we're going to be looking in through the output terminal, so right here. And it might be tempting to say that Z out, which maybe I should be a little bit more precise, call this Z out up here. It might be tempting to say that this is RE in parallel with these two resistors here. But this is not actually correct, and it all comes down to kind of this base current and how it can be a little bit tricky to work with. So recall, to find the output impedance, we can also use the test voltage, Vx, and then what we're going to say is that the output impedance is equal to Vx divided by Ix, or the current coming out of that test voltage. So down here, we're going to apply that test voltage, and we're going to set up a KVL from Vx to Vn. Now to do this KVL, we can really do this in two ways, and it gets a little bit confusing, potentially the most confusing thing in this course. So we're going to be looking at essentially this loop here, and if we draw that out, what we get is the following, and get ready for some confusion. Now in this circuit, there's a few things we can do, and what we're really trying to do is figure out what IB is. And if we label it as we did above like this, the circuit really doesn't make sense, especially if we carry through with that input polarity. So instead, what we're going to do, we're kind of going to ignore that input polarity, and we're going to redefine something, call it IB prime. Now notice that IB prime is equal to minus IB, and that's the base current from above. Now we do this because then things kind of get a little bit easier. If we do a KVL here, we can say that Vx minus IB prime R pi minus IB prime times RS prime, that's going to be equal to 0, or simply that IB prime is going to be equal to Vx divided by R pi plus RS prime. Now we know that that's going to be equal to minus IB, and this gets us to the term right here. We said that the base current is equal to minus Vx divided by RS prime plus R pi. So we found our base current, and now what we're going to do is set up a KCL at the emitter node, so point E. Now because we just defined what IB is, we can plug that in for this term, and we can simplify it as Ix is equal to Vx divided by Re plus beta plus 1 times Vx divided by Rs prime plus R pi. Or what we can do is simply say that we have Vx divided by Ix, which is our generalized output impedance, and that's going to be equal to this term here. So now we can find the output impedance. Nevertheless, we can set up a simulation for this amplifier. So in the green here, we have our output, and in the blue here, we have our input. Notice there's a slight gap between the input and output. Again, we would not expect that gain above unity. So this kind of goes to show that through all of this analysis, we do actually get a circuit that makes sense when we simulate it. And we actually have one more amplifier we're going to look at for the NPN BJT. It's going to be the common base amplifier. If you learned anything new or useful in this video, please like, comment, share, subscribe. We'll see you in the next video. Thank you for watching.